Today we're going to start a new set of lectures, 2 lectures on fluids, and they will be divided into 2 topics. The first topic will be static fluids. The second topic will be fluids in motion or dynamic fluids. In static fluids, we will be discussing 4 principles or 4 parts of fluids at rest. The first of these is the concepts of density and pressure. Hopefully this will be a review for you guys. We have done this before in basic science class, and I think that you should find it fairly easy and straightforward as we review this. The second will be Pascal's principle, which is the idea that a force exerted on a closed fluid is distributed equally throughout that closed fluid. And it is the principle for many of our mechanical lifts and hydraulic lifts. The third principle is Archimedes' principle and the idea of buoyancy. And then lastly, we will be talking about cohesion, adhesion, capillary pressure, and surface tension. So let's take a look at some of the factors that impact how various materials react or act in this universe. Now on the left here we have atoms in a solid, and you will notice that because of the way that the bonding forces have been set up, that the atoms in a solid always have the same neighbors. They are held near to those places by forces which have been represented here by springs. The atoms are essentially and always in contact with each other, and the rock that's shown here is an example of a solid. It retains its shape because the forces holding those atoms together cause it to retain its shape. Now B is a fluid, and fluids or liquids are also in close contact in terms of their atoms. However, the forces are lax enough to allow them to pass over or slide over one another. They're strong enough to resist attempts to push them closer together or pull them apart, and so they do hold them in close contact, but they are capable of sliding across one another. Water, of course, is an example of a liquid, and water will flow, and it remains in an open container because of the forces between the atoms. And then on the right we have gas. And gas atoms are separated by considerable distances. They have very little in the way of attractive forces between each other, and they move quite freely. Gases, if left on their own, do not aggregate together and do not hold any particular shape. They have to be held in a container in order to prevent them from moving away freely on their own. Now this is just to emphasize the concept of density. A ton of feathers and a ton of bricks have the same mass, but a ton of feathers makes a huge pile, while a ton of bricks is a very small pile, and that's because the density is different. Now that is a simple concept, but sometimes people forget the idea of density and mass and weight. One thing I will caution you during this lecture is to make sure that you separate the idea of mass and weight or force. There are weight densities and there are mass densities, and most of the time we will be talking about mass density, which is a mass unit divided by a volume. But sometimes we will be talking about a weight density, and in that case you have to keep that in mind. Now density is shown by this formula. Rho equals the mass divided by the volume. Now obviously you can manipulate this equation in order to show that mass, for example, is equal to rho times the volume, or mass is equal to the density times the volume, and the volume is equal to the mass divided by the density. Now there are many units involved when we talk about density. The SI units for density, that's the System International units. And when we talk about density without a particular adjective to describe it, we're always talking about mass density because it always fits this equation. And so the SI units for mass density are kilograms per meter cubed. Now another one that's commonly used is grams per centimeter squared. Now the English, in their usual way, is completely different. Now if it was going to be a mass density, it should be something called a slug, which is a unit of mass in the English system. But because very few people work with slugs, they actually talk about pounds per cubic foot. But pounds per cubic foot is not a mass density. It is actually a weight density because pounds is a unit of weight. And if you divide the weight of something in pounds by 32.2 feet per second squared, you get the slugs or the mass of that object in the English system. So that's one of the confusions that occurs with the English system and one of the crossovers that occurs that you have to be careful of during this chapter. Pressure, on the other hand, is force over a particular area, or force per unit area. P here is pressure, F is force, and A is area. And here are some units that are reasonable to keep in mind when you think about pressure. Now remember, pressure is a force unit, so it's newtons in the metric system, newtons per square meter, and the newtons per square meter is also called the Pascal. So if you see something in pascals, that's basically the SI unit for pressure, and that what they're talking about there is the force per unit area, and the area being meters. Others that you may see include dynes, which is what the D here stands for, and dynes are grams mass times the acceleration of gravity in centimeters per second squared. So it's grams times 980 centimeters per second squared, and that's what a dyne is. And so dynes per centimeter squared is an attempt to keep the units consistent with each other. And then the English here have it right this time because it is pounds, because that's a force unit per square foot. Now when a person is poked, they are poked, let's say, with the same force. And in one sense, in the first sense, A, they're poked with a finger, which has a fairly large area. Therefore, the poke might be a little bit irritating because the pressure is fairly small. But if the area is very small, then the poke becomes much more irritating because the pressure becomes large and the skin is actually broken. In this example, the force in both of these situations is identical. But because one has a large area and the other has a small inner area, and that the pressure is inversely proportional to the area, one has a small pressure and the skin remains intact, and the other has a very large pressure and the skin. The pressure inside this tire exerts forces that are perpendicular to all the surfaces that the gas inside comes in contact with. And so what you see here are arrows all the way around the circumference of the inside of the circle where the rim of the tire is, and the outside of the circle where the tread is. And the force exerted throughout, the pressure exerted throughout, is the same. And so at every point along the way, the pressure is the same. And what the expanded view is the needle, which allows for filling of the tire with air. And what you can see is even within that needle, the perpendicular pressure is the same. And so if you push on the top right here with a pressure that's equal to this will open and allow you to put more air in. But you have to exceed that pressure before it will open. The static fluid, if you put fluid in here, there are no shear forces involved, and that's important to know. Now the purpose of this drawing is to show you that the pressure of the water here is exerted perpendicular to the swimmer, and it's on all sides. Now one thing that is important to notice is that these arrows are smaller than these arrows. And the reason that these arrows are smaller than these arrows is the depth of the water involved is different here than here, so that there's less water, thus less force for every unit of area on this side of the swimmer compared to this side of the swimmer. And this is why a swimmer is buoyed up in the water as he swims along. The forces are larger underneath because of the greater depth, and that causes what we call the buoyant force and reduces the weight of the swimmer. But the swimmer does not float to the surface because his own weight is greater than the balance between these two forces. And we will talk about this some more when we talk about Archimedes' principle. Now let's do a couple of problems related to this, what we've talked about so far. And I'm going to reduce this slide so that you can see the problems and so we can work them here. And the first problem states a fairly obvious principle. It says a common way to find the density of an unknown object is to weigh it and then measure its volume by submerging the object in water. So if you have an object that has a mass of 240 grams, you drop it in water and you collect the water it displaces, and it displaces 89.0 centimeters cubed of water. What is the density of the object? Well, the way we would go about doing that is, first of all, I have to tell you that the rho of water is 1.000 grams per cubic centimeter. And so if you know that, then you know that the mass divided by the volume is equal to rho. Therefore, V is equal to the mass divided by rho. If you put the number in there, you have 89 divided by 1. So the volume of the rock is 89.0 centimeters cubed. Okay, so that is the volume of the rock. So what is the density of the rock? Well, again, here's your formula for density right here. It's mass divided by volume. In this case, the rock has a mass of 240 grams and a volume of 89 cubic centimeters, and so the density here is 2.70 grams per cubic centimeter. Don't forget your units. So that's the answer to our first problem. Our second problem, suppose you have a coffee mug with a circular cross-section and vertical sides. What is the inside radius of the cup holding 375 grams of coffee when it's filled to a depth of 7.5 centimeters? Assume that coffee has the same density as water. Well, first of all, we know that mass over volume is equal to density. Therefore, volume is going to be mass divided by density, which is 350 grams of water divided by 1, or 350 cubic centimeters of coffee. So that's how much coffee we have. We also know that the volume of a cylinder is pi r squared h, so that h will equal, r will equal v divided by pi h square root. And then we put these numbers in, 350 cubic centimeters divided by pi, and 7.5 centimeters was the depth, taking the square root of all that. And if you do the math on a calculator, you get 3.85 centimeters in radius. So that's the first problem, 2 problems. Here's a couple more problems, working with pressure now. It says the pressure exerted by a phonographic needle is surprisingly large. If the total mass is 1 gram and the radius of the needle is 0.200 millimeters. What is the pressure in newtons per square meter? Well, this converts, remember newtons is square meters, so we got to convert this to square meters. This is going to be 2 times 10 to the minus 7th meters. Excuse me, 2 times 10 to the minus 4th meters. Math's a little off there. The area, therefore, is going to be pi r squared, which will be pi times 2.0 times 10 to the minus 4 squared. So the area here is 1.26 times 10 to the minus 6th meters squared. And we know this is 1 gram. 1 gram is 1 times 10 to the minus 3 kilograms. And so pressure is force divided by area, which is going to be mass times gravity over area, which is going to be 1 times 10 to the minus 3rd times 9.8 divided by 1.26 times 10 to the minus 6, and you do all of that and you get 7.80 times 10 to the minus 4 or plus 4 newtons per meter squared, or pascals. One final problem before we wrap this part of the lecture series up. Nail tips exert a tremendous pressure when they're hit by hammers. That's why they penetrate wood. What force is exerted on a round nail tip whose diameter is 1 millimeter if the created pressure is 3 times 10 to the 9th newtons? Again, force is equal to pressure times area. So that's by converting. If you convert this, you can use this, the areas go over here, and so you have this formula. And so what you need here is pressure times, and the area here is going to be, again, pi r squared. So you're going to have 3 times 10 to the 9th times pi times 1 times 10 to the minus 3rd squared. And you do all that and you get 9.42 times 10 to the 3rd newtons. So that's the force that's exerted on the nail tip when you hammer it with a nail. So that completes this part of the lectures. When we return, we'll begin talking about some of the more complex